Hi everyone, and welcome to Austintronics. In the last two videos, I gave a general overview of typical software components you'd find in operating systems. I also showed you what specific OS components I plan on using for RoboDog, and how all the software components interact and flow with the Zinc chip architecture on the Zybo board. We also installed Xilinx tools and created a bitstream in Vivado for the PL, and a first stage bootloader in Vitis for the PS. We also generated the rest of the OS components like the device tree blob, U-boot, and kernel binaries, as well as the root file system, and even went over how to partition and format your SD card so the Zybo board knows how to grab all the OS components from it. So now that our SD card looks good, let's start getting all of the OS components on it. First thing we'll want to do is go back to Vitis, right-click the application project, and select Create Boot Image. This wizard that just popped up will create a file called boot.bin, which combines your first stage bootloader, your bitstream, which is design1 wrapper.bit, and your uboot.elf file, which we'll need to add. You do this by pressing Add, Browse, go to your uboot Xilinx directory, and double-click uboot.elf to select it, then press OK. You'll see uboot.elf add to the list. Order here is important, so make sure that your first stage bootloader is first, the bitstream is second, and uboot is third. This wizard will also create another file located in your _IDE directory called RoboDog app system.bif, which is a configuration file that shows how the boot.bin file is laid out. Remember this location because we'll need to reference it later. Next, click Create Image, and a few seconds later, you should see a boot image generated successfully in your console if everything went well. In your platform project, double-click on platform.spr, go to Linux PS7 Cortex A9, click Browse, where it's looking for a BIF file, and make sure you go to that _IDE directory we were looking at earlier, and select the BIF file. Next, let's locate the boot components directory. You can just select the same directory that the BIF file was in, which was boot image, then click Open. And that's it for the platform.spr file. We don't need to add anymore. The other config sections are for other features of Vitis that I don't plan on using at this point. Now, make sure you select your application project, then press the hammer, which will build both the platform and application project for you. Once everything's done building, you can find the output files that you need in this debug directory. Inside, you'll see an SD card directory. The readme.txt file just says to copy the contents of the directory into the SD card, so we'll do just that. We'll first go to the 34 megabyte partition, which is the boot partition. Remember, this will contain everything except the root file system. Now let's copy the boot.bin and robodog app.elf files to the SD card. The robodog app.elf is just our Hello World program, and we don't really need it on the SD card for it to boot, but it doesn't hurt to have it here. Once the OS is fully booted, I'll show you how you can grab the robodog.elf file from this partition so you can run it. Let's open up a new tab here and go fetch our Linux kernel image, which is in Linux, Xilinx, Arc, ARM, boot. Remember, we want the uimage version of the kernel binary, so I'll copy that with Ctrl-C, then Ctrl-V to paste it into the boot partition of the SD card. Next, while we're in the boot directory, let's go into the DTS directory and grab the Zinc Zybo z7.dtb all the way at the bottom here. Again, I'll use Ctrl-C to copy and Ctrl-V to paste. Next, we're going into the Pocky build directory under the build toaster 2, temp, deploy, images, Zybo Zinc 7, and we'll grab this uenv.txt file, which is the uboot environment text file. Now, this is completely optional, and you should still be able to boot without this file, but it's nice to have since it allows you to easily control some parameters of uboot from a text file instead of manually configuring things with uboot's interactive shell. You can see that this text file was also one of the kernel artifacts that was generated when we built our image, so you could just click that link and get it from there too. Since I have this file here though, I'll copy this file, then I'll paste it in the boot partition like I did with the others. This is what the uboot environment file looks like. There are a few quick changes I'd like to make here since we're using this config file for uboot. One of them is where the device tree image is pointing to. Right now, it is zinc-zybo.dtb, when it should really be zinc-zybo-z7.dtb, which is the name of our DTB file on the same partition. So these names here need to be exactly the same, otherwise uboot will yell at you. The last thing I wanted to add here is the boot command, which will overwrite whatever uboot's default boot command is. I like having this in the file so I know exactly what uboot will run to start the process of getting the Linux kernel loaded. Here, I'm just running the boot kernel, which in turn runs this line, which will run other commands using other uboot environment variables and so on. And that's it. These are all the files we need for our boot partition, plus the optional uenvironment config file and the RoboDog app program that just prints hello world. Next is the root file system partition. Let's go back to the zinc Zybo 7 tab under the Pocky directory. Your file system will be compressed into a tar.bz2 file with the same name you gave your custom image plus the machine name that you built your root file system for. In my case, it will be robodog image minimal dev zybo zinc7.tar.bz2. And here's the full path where it's located. You'll want to copy this. So our current goal is to extract the components of the tar.bz2 file into the root file system partition. I'll do this by going to the root file system partition, right-clicking, and opening a terminal at this location. Then I'll run the following tar command on that tar.bz2 file with a -c /, which will tell it to empty the contents into the current directory that we are in. And within a few seconds, you'll have your custom root file system on the partition. Once I hit the eject button on the side, you may see this pop up. Your computer is still writing out all the contents to the SD card, so just give it a few seconds and it should tell you it's okay to remove from your computer. And now we're good to go. We can now unplug the USB adapter from the computer, take the micro SD card out, and insert it into the Zybo board. But before I turn it on though, let's get a Minicom session going. The Minicom program will allow us to interface with the board via the USB cable. If you don't have it installed directly, you can install it with your package manager. I'm using apt on my Ubuntu computer, so for me, it would be sudo apt install minicom. Once you get minicom, you should type in sudo minicom-s. The -s tells minicom that you want to configure the tool first. Go down to the serial port setup and make sure that your serial device is pointing to the correct USB port. The Zybo board has a 2-channel USB, so you should actually see 2 COM ports show up on your computer when you plug it in. The one that you want to connect it to is the second one, since that's the Linux debug console. Because the only thing I have plugged into my computer is the Zybo board, the COM ports are enumerated on my computer as /dev/tty USB 0 and /dev/tty USB 1. This may not be the case for you though if you have anything else plugged into your computer that registers as a COM port. So make sure the USB you're actually pointing to for Minicom is the second channel for the Zybo board. About half a second after turning on the board, I'll push exit on the Minicom so that I can connect to the COM port and start reading the contents that the OS components are spitting out. And stop. I'll freeze the video here for a second because there's a couple things I want to point out. Notice that the program at the top says uboot. That's right, all the text you see here from this point and below is generated from uboot running on the CPU. This means that the boot ROM code and the first stage bootloader has already ran and loaded the bitstream into the PL. The reason you don't see any first stage bootloader print statements before this is because, well, it's just not configured to output print statements to this port. But if you want it to be though, for example, let's say that your board is having issues booting into uboot and you want to see if the first stage bootloader will give you more insight into the problem, it's possible to make proper configurations in both Vitis and Vivado inside the Zinc core to make sure that the output from the first stage bootloader is being pushed out this port. I also wanted to point out this countdown timer here. If you hit any key on your keyboard before the counter counts all the way down, you'll go into uboot's interactive console where you can configure different settings, change the environment variables, tell it where to fetch the kernel, and so on. But we don't need to go into that console and modify any of that stuff since uboot's already doing exactly what we want thanks to that u-env.txt file we placed in the boot partition earlier. As for the bitstream that's flashed on the PL, here is me toggling the switches. And check it out. You can see the LEDs light up, just like how we designed it in the digital logic. Alright, let's continue the countdown that uboot is doing and see what happens next. And stop. Okay, so there's a couple more things I wanted to point out. Soon after uboot's timer counted all the way down, uboot goes out to fetch the kernel and, check this out, it places it into RAM at hex 8000, exactly where we told it to when we built the uimage binary. And, of course, the entry point where the CPU should start its execution when uboot stops running is at hex 8000 in RAM. Another thing I wanted to show here is that the device tree blob, or DTB, is also in RAM at this location for the kernel to use. Also, here at the bottom, you can see that the last thing that U-boot prints out before it stops running is starting kernel. If we fast forward less than a second later, we can see that Linux is now currently running on the CPU, which means all of these print statements are now coming from the Linux kernel and not U-boot anymore. We can also see which version of Linux we're running, along with additional information like the computer name we built the Linux kernel source code on, which ARM processor the Linux kernel is running on, and so on. Let's continue booting the rest of the way. You'll also see that there's some LEDs that flash right here. These LEDs correspond to the sending and receiving of data through the COM port. Okay, we're at the login now. The default username will be root. Let's look around here and get the lay of the land. Exactly what you'd expect to be in the slash directory. Let's do Python 3 to make sure that that's on the system. And yep, that looks good. Now let's test Dropbear to see if we can SSH in over the Ethernet instead of using the USB cable. I'll open up another tab here. And let's copy the IP address of the board with ifconfig. And I'll run the SSH command, which is SSH, then the username, which is root, and then the IP address of the board. So if you're not constantly rebuilding root file systems and placing them on the SD card like I am, you won't get this warning. The reason I get it is because whenever the OS boots for the first time, Dropbear makes encryption keys and places them on the root file system for validating the SSH session. And the fact that my encryption key changes because I'm running a new root file system, but the IP address stays the same, the SSH client on my host freaks out. To remove this warning and actually SSH in, you can simply use the ssh-keygen command to remove the outdated encryption key. I'll try re-SSHing in. I'll say yes here to restore the new encryption key on the host, and congratulations, we're now successfully logged into the Zybo board over the network. Is there more things that I can add to the root file system with Yocto to improve security? Absolutely. But for now, the point of this video is to get you familiar with all the main OS components to help you get an embedded system platform like the Zybo board up and running. Now, if there's enough interest in exactly what software packages I end up placing on my root file system for the actual implementation of RoboDog, let me know in the comments and I can make a video on it. Speaking of software packages, what if we wanted to install a software package, for example, ethtool, that we forgot to put on the root file system when we first built it? You have two options. You can either repeat the process that we did for adding the software packages to your custom image, rebuild it, and replace the root file system partition on your SD card with the new file system. Or a more dynamic way is to build the software packages with Pocky and use your package manager to install those packages. Because you've already seen the first way, I'll show you the second way now. Let's go back to Toaster and go to our main project page. Go to software recipes, and let's search for the software package that we want, which is ethtool. Then click Build Recipe. This should only take a minute or two. Now that it's done building, let's go back to that directory where we got our root file system. Go back up the directory to the deploy and look inside RPM. You'll see three main directories, which are Cortex A9 T2HF Neon, NoArc, and Zybo Zinc 7. You want to make repos out of all three of these so that your OS package manager can grab software packages from them. This is because the Yocto project is placing the software packages in these directories. So whenever you build the software package in Yocto, this is where it's placing them. Let's create our first repo starting with the Cortex A9 directory. Once inside, right-click and open a terminal in that location. We're going to be using the Create Repo tool. So if you don't have it installed on your computer, you can type in sudo apt install create repo. Once that installs, run the command create repo /. And after a few seconds, the create repo command placed the proper metadata files within this directory to make it a repo for you so that you can grab software packages from it. We'll want to do this with the other two directories as well, so I'll go up a directory and go into NoArc and do the same thing. And again, the same with the Zybo Zinc 7 directory. The last thing that we need to do so that our OS package manager on the Zybo board can find these software packages is to create an HTTP server starting in the RPM directory. Python has a built-in HTTP server, so once we've gone up one directory into RPM, I'll simply run python3-m in quotes http.server and run this HTTP server at port 8080. And once you press enter, you should see something like this. Let's go back to our SSH session on the board and try to install ethtool now with the DNF install ethtool. And it failed. If something like this happens to you, try going to your package manager configurations to investigate. For DNF, this is under /etc/yum.repos.d. You'll see 3 .repo files that should match the name of each of the directories you turned into a repo on your host. Let's go into the Cortex A9 one first. Can you spot what needs to change? Our HTTP server is running at port 8080, but the base URL for where DNF is searching for the software packages is at port 8000, which is the default port if nothing is specified. We could change the HTTP server to port 8000, but that's actually the port that Toaster is running at, so let's change these configuration files to use port 8080 instead. And let's make sure we change the other 2 files as well. So you might be wondering why the configurations for the package manager were set to what they were. Remember the build environment variables we entered in on the Toaster interface? This is how Pocky knew what IP address and paths should be used in these .repo files. If I would have used port 8080 for the IP address when I passed in the variables to Toaster, then I wouldn't have had to change it here in the configuration files. But hey, now you know how to configure the package manager on the OS and in Toaster. And with that out of the way, let's try to install ethtool again. You can see the activity on the HTTP server, which is a good sign. And there we go. We now have ethtool installed. Let's drive the point home and get one more software package for our OS. Let's get PCI utils. This is a software package that has a command line tool for probing or checking the status of PCIe devices on your PCIe bus. Let's start by going to our homepage, and like usual, let's go to software recipes, type in PCIe utils, and go ahead and build the recipe. After a few seconds, we now have PCIe utils built. Now we need to update our RPM repos since we just added a new package to them. Generally, the majority of the software packages will be added to the Cortex A9 repo, but I like to update all of them just in case. You can do that by just rerunning the create repo command for each directory like I'm doing here. One last thing I have to do, otherwise the package won't be found on the repo, is that I have to clean the cache of the DNF package manager on the OS. You can do this with the dnf clean all command. Now, just to show that we don't already have the command lspci, which comes with the PCI utils package, I'll try running it now. Now, I'll dnf install PCI utils. And that's all there is to it. Now we have PCI utils and ethtool. Now, one of the questions that I know will probably be asked is, why do I have to use the Octo project to generate the software packages? Why can't I just install packages from the same repositories that my Ubuntu, Fedora, CentOS, or whatever machine is using? From my experience, I've had mixed results with this, and generally they weren't good. First, you need to make sure that you're pulling from repositories that match the architecture that you're on, which in this case is an ARM v7. But second, you're not running any of those distributions. This is a custom distribution that you made from scratch, so creating and managing your own software package repositories like what we're doing here guarantees that the software packages that you're building will work for your own OS distribution. But for anyone ambitious enough who'd like to pull software packages from a mainline repository for your own OS, or think they have a better way to install software packages than what I just demonstrated, please let me know in the comments. I'm always interested in learning better ways to do stuff like this. One of the last things I wanted to show on the Zybo board was our Hello World RoboDog application running that we created in Vitus. Let's do an ls/dev to take a look at what the memory devices we have connected. This MMC BLK0P1 here is the first partition of the microSD card. This is where we put our Hello World RoboDog app in, so let's mount this to a folder so we can access its contents. I'll go to the home directory where nothing is currently and make an empty directory called tmp or temp. I'll then mount the first partition of the SD card to temp with the built-in mount command. Now, if you look inside temp, you'll see everything we placed inside the first partition of the SD card is here. Anything you modify, add, or delete in this folder will reflect on the SD card, so be careful. If you delete your uimage kernel binary, for example, U-boot won't be able to load the kernel and you'll have to re-upload it to the SD card. Let's cd into temp and execute the RoboDog application. Hello world. Exactly like what we expect. When you're done accessing the contents of the SD card on the root file system, you should unmount it with the command umount temp or whatever folder you use to mount it. By the way, now that we have Ethernet working, you don't have to keep taking out the SD card and uploading your application onto it whenever you want to make updates to it with Vitis. Once you've built the application, you can simply send it over Ethernet using an SCP command. If you're unfamiliar with how that works, you can check the resource links that I'll put in the description so that you can learn more about it. For those of you who want to customize your U-boot, Linux kernel, or DTB, I'll briefly show you that now. So why might you want to customize these OS components? Well, there could be many reasons. Maybe your U-boot or kernel is crashing and you want more verbose print statements to track down the error, or maybe you need a driver that's not built into your U-boot or kernel images by default. There's these and several more reasons why you might need to configure these OS components. Let's start with U-boot. First thing to do is open a terminal in your U-boot directory. Then run the command make menu config. After a few seconds, you'll see a menu you can go through. All of these are different options and settings you can implement in U-boot. If you highlight any one of them and press enter, you'll be able to select or deselect the configuration. The entries that have arrows are categories. You can go into these categories by pressing enter when you have them selected. And you can go out of the categories by selecting exit at the bottom. If you like your configuration, you can save it by selecting save at the bottom, and the config contents will be pushed to a .config file located at the top level in your U-boot directory. I'll Control-C out of this menu since I don't want to overwrite my existing .config file. In order to see that the file's there, you'll have to use ls-a since it's a hidden file. Whenever U-boot is building, the build tools will always look for the .config file so that it knows exactly how to build U-boot. So all you have to do to get the changes to take effect is to rebuild U-boot. Once you have the U-boot binary built, go to Vitis and make sure to clean and rebuild the application project. This will create a new boot.bin file for you so you can just update the SD card with it. The configuration process for the Linux kernel is actually pretty similar. If we open up a terminal in our Linux kernel source code directory and do an ls-a, you can even see that it uses a similar convention for the configuration file with a .config. In fact, if we type in make arc equals arm menu config, we'll be presented with an almost identical looking configuration menu. And just like with U-boot, you can go through and select what you want in your kernel the next time you build it, as long as you've saved your configuration to .config. Last up is the DTB, or device tree blob. Now, from my experience, making changes to the DTB is almost like an art. It's not like U-boot and the Linux kernel configurations. It can be pretty delicate, and you really need to know what you're doing. By making edits to this file, you're essentially telling various source code and drivers throughout U-boot and the Linux kernel to configure the specific hardware in the Zinc chip and on your board in a very specific way. Most of the time, when you need to go in and edit your DTB, it's probably because you're making your own PCB, but it could also be because you want to initialize some digital logic that you made in the PL. I could probably make an entire video on all the nuances associated with the DTB file, but that's a little bit outside the scope for this video. For now, I'll just get you acquainted with some of the basics. For starters, you wouldn't want to make changes to the DTB directly since it's a binary file. You'd instead make changes to the DTS, or device tree source. The program that converts the DTS to the DTB is called a device tree compiler, or DTC for short. If we open up the Linux kernel source code directory and go to scripts, DTC, you'll see the DTC program here. I'm going to copy this path since we'll need to reference the DTC later. Let's make our way to the DTS I'm using in the Zybo board in arc, arm, boot, DTS. The Zinc Zybo z7.dtb is what we're using on the Zybo board. And the source for that is Zinc Zybo z7.dts. Let's take a peek inside and see what it looks like. So not too long, right? That's mostly because there are a couple of include files here at the top that abstracts a lot of the source code away from you. Instead of finding these files somewhere in the Linux directory, we can just reverse compile the DTB into a DTS file. You can do that by using the DTC program I showed you earlier in the scripts directory. It would look something like this. This is saying execute the DTC with a DTB as an input and a DTS as an output. And the name of that output DTS file will be zzz.dts, just so we can find it easier in the file manager. And the DTB file that we want to reverse compile is zinc zybo z7.dtb. Let's push enter. And now when we go back, we can see that there is a zzz.dts file. When we open it, We can see this is much longer than the other DTS files since this is a single file now that contains everything that was inside the DTB. To me, this is a lot easier to edit than bouncing around in different files trying to find what you're looking for. It's also nice knowing how to reverse compile the DTB in cases where you may not have access to the original DTS that made it. Let's take a look at a random location in this file. These blocks of code are called nodes. This node here tells me that there is some PMU device, which stands for Power Management Unit, that physically exists somewhere in the system, and to access it, the software, whether that be in U-boot or the Linux kernel, or both, need to write and read from physical address of hex F8891000. I also know that by looking at this, that the interrupts associated with the PMU are coming in at the pins on the zinc chip marked at these hex values. If you don't understand what any of that means, don't worry about it. You shouldn't really need to modify anything in the DTB for this board anyway, since it's already been done for you. But for more advanced embedded developers out there, or for those who are just curious and want to learn more, I'll put a link about the device tree usage in the description. Alright, so let's say that you've made your edits in the DTS. To compile your DTS to a DTB, it's almost the same command, but instead the input would be a DTS and the output would be a DTB. You'd also change the name of the output file you're creating to be a .dtb file type. And lastly, the DTS file you want compiled. And here's our compiled DTB file. And just to make sure reverse compiling and normal compiling give you the same output, take a look at the size of the DTB that we just created. We see that it's 11.2 kilobytes. We would expect the other DTB file to be the same size since we didn't actually change anything, and it looks like it is. But let's take it a step further and just make sure that it's 100% the same as the old DTB. Let's do a diff in the command line just to compare the two files. And diff returns nothing, which is exactly what you'd expect to see if the files are a perfect match. The last thing I wanted to cover is how you can get all the software I covered in this video through my GitHub. My GitHub link is in the description. When you go there and grab the link to clone the RoboDog repository, you'll have to use the argument recurse submodules, otherwise you won't get the U-boot, Linux kernel, and Yocto project directories. This is because those projects all exist in different GitHub repositories, and the recurse submodules command is just letting your Git tool know that you want to download all of them from their respective repositories. Once you download everything, all the software will already be on the correct branches and tags that I use throughout the video, so if you're following along and you download my RoboDog repo, you won't have to call any of the branch or tag specific checkout commands when I first pulled the repos. As I get farther along with the design, I'll be updating the RoboDog repo on GitHub for anyone interested, so be sure to check out the README file for the latest instructions on how to download and interact with the project. Anyways, that's going to do it for this video. If you found this content useful, or even if you didn't, let me know why in the comments below. If you want quicker updates on the RoboDog project, or just want to come hang out and talk about robotics, you can join me and several others on their Awesometronics Discord. Thank you all so much for watching and all the support you've given me over the months while working on this project. And as long as you guys keep enjoying these videos, I'll keep making them. So stay tuned for the next one. Thanks everyone.